Okay, so I'm going to record Newton's laws. Coulomb's laws. Practice problem. Question 1 says, given the mathematical representation of Coulomb's law, and it gives you the value for K, describe in words the relationship among electric force, charge, and distance. So what I said was the product of the charges which is Q1 times Q2, is directly proportional to the force, F, the square of the distance of separation between the charges is inversely proportional oops, misspelled that. Hang on, got some trouble here. Inversely proportional to the force. So that was question 1. Question 2 said, by how much does the electric force between a pair of charged bodies diminish when their separation is doubled? So 1 over 2 squared is 1/4. So force new is 1/4 of the old force. If you triple the distance, which is the second part, the new force is 1/9 of the old force. Okay. Question 3. Let's try to do practice question 3. So we got an electron and proton. So the charge of the electron equals the charge of the proton in magnitude. Now we know they're opposite in sign, but the charge magnitude is both 1.6 times 10 to the negative 19 Coulomb. I have no idea what that is, so we're going to get rid of it. And they are separated by a distance of 5.0 times 10 to the negative 11 meters. And the mass of a proton is approximately 1.67 times 10 to the negative 27 kilograms. And the mass of the electron is approximately 9.11 times 10 to the negative 31st kilograms. Okay. Part A says, using Newton's law of universal gravitation, calculate the gravitational force between the electron and the proton. So the force of gravity is big G, M1, M2 over R squared. So that's 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared. Then I'll multiply that by the mass of the proton. And then comes the mass of the electron. I only use 9.0 times 10 to the minus 31 because that's what the problem actually said. It's technically 9.11, but that's all right. And they're separated by a distance of 5.0 times 10 to the minus 11 meters. Do not forget to square that, please. So the force of gravity I got was 4.13 times 10 minus 47 newtons. And you might get something a little different right there because when I did the math, I actually did 9.11. So that's what I was trained to use as the mass of the proton, or electron. Okay, so there's our universal gravitation, force of gravity. Part B says, find the force of attraction between the two particles. So the electric force, Coulomb's law says it's K Q1 Q2 over R squared. K is 9 times 10 to the 9th, Newton meter squared over kilogram squared, over Coulomb squared, sorry. Q1 and Q2 are equal, so they're both 1.6 times 10 to the minus 19 coulombs. And I'll just square that, so that would be Q1 times Q2. And they are separated by a distance of 5 times 10 to the minus 11 meters squared. When I did that, I got 9.22 times 10 to the negative 8 newtons. Okay, and then it said, part C, how many orders of magnitude greater is the electric force between the two particles than the gravitational force? So I said, well, the electric is this, the gravitational is this, so 10 to the 39th times greater. The electric force is 10 to the 39th times greater than the gravitational force. And then it says, how important are the gravitational force effects in this case? They are so minute. We can't imagine. All right, that was number 3. Number 4 says 2 charged spheres are on a frictional horizontal surface. So there's sphere 1 and sphere 2. And it says that one of them is plus 3 microcoulombs and one of them is plus 6 microcoulombs. And it wants you to sketch the 2 spheres showing all the forces on them. Make the length of your force arrows proportional to the strength of the forces. All right, so we have gravity pulling down here. And we don't know how their masses compare, so we're going to assume that they're the same. So we have the force normal. And I'll try to make them the same. Right? And then we have the force of gravity between this one and this one. But I'm going to go with the fact that it's so tiny that we're not going to worry about it. And then we know that this one is pushing this one away. And this one is pushing this one away. And these should be about the same length, because the force is the same. And then I think that's it. I could put the gravitational attraction between them, but like I said, it's typically so tiny, 10 to the minus 47. We're not going to worry about it. Okay. Number 5 says 2 positive charges of 6 microcoulombs are separated by half a meter. Draw a force diagram for each of the charges, considering only electrostatic forces. What is the magnitude of the force between them? Is it attractive or repulsive? So here are my 2 charges. They are both positive 6 microcoulombs. If I'm reading that correctly. And so this one is pushing the one on the right away. This one is pushing the one on the left away. These vectors should be the same length. Magnitude of the force is K, Q1, Q2 over R squared. And we know that they're half a meter apart. So we have 9 times 10 to the 9th. Newton meter squared over Coulomb squared. Q1 and Q2 are both 6 times 10 to the minus 6. So I'm just going to square that value. And then they're separated by 0.5 meters squared. When I did that, I got the force to be 1.296 newtons. And I said it was repulsive, because they were both positively charged, so they don't like each other. All right. Let's scoot on to number 6. Number 6 says a negative charge of 2 times 10 to the minus 4 and a positive charge of 8 times 10 to the minus 4 separated by 0.3 meters. So R is 0.3 meters. What is the magnitude of the force? Is it attractive or repulsive? So this one was my 2.0 times 10 to the minus 4 Coulomb. I'll call that Q1. And then Q2 is 8 times 10 to the minus 4, if I remember, yep. 8 times 10 to the minus 4 Coulomb. And we want to find the force. Well, the force is 9 times 10 to the 9th. Newton meter squared over Coulomb squared. And then multiply that by 2 times 10 to the minus 4 Coulomb. And 8 times 10 to the minus 4 Coulomb. And they're separated by 3/10 of a meter. Don't forget to square that. So I'm going to have, I got 16,000 newtons. And I said it was attractive. Alright. So let me see if that makes sense. This one seems very tiny compared to that one. I'm going to stop, check my math, and then I'll record the next part.